And kinetic. Static friction is the friction that resists the initiation of motion. If you place a block on a table and try to very lightly push it into motion, it will first resist that motion because of the frictional force operating in the direction opposite the applied force of your push. You can push harder and it will still remain still, because the frictional force will always precisely oppose the applied force. Static friction will increase until the magnitude of the applied force exceeds the maximum static frictional force the table can exert. Then the force of the push can no longer be cancelled out, and the block will begin to accelerate. This frictional force is proportional to the normal force, so the heavier the object, the greater the normal force, and the greater the frictional force. This is because as the weight of the object increases, the harder it presses down on the surface, which will increase the number of contact points between the object and the surface. The static frictional force will be anywhere from 0 to the maximum possible value, depending on the forces operating on the object, since the static frictional force will be equal to the applied force until the maximum is reached. The magnitude of this maximum can be calculated this way. F max is equal to the coefficient of static friction times the magnitude of the normal force. This coefficient, represented by the Greek letter mu, is unitless and unique to the surface in question, and we have tabulated these coefficients for a variety of common surfaces, like glass, steel, wood, and rubber, and the various combinations thereof. As we said, once the applied force exceeds the maximum static friction, the object will begin to move. Bear in mind that this equation involves scalar quantities, not vectors, and therefore implies nothing about direction. As we said, static friction opposes the initiation of motion, but once an object is in motion, it is now moving against kinetic friction. This is the force that opposes relative sliding motion. Kinetic friction is always lesser than static friction, which you will notice if you try to push any object across a surface, like a heavy box across the floor. It will be more difficult to get the box going than it is to keep it moving once you've started. There are coefficients of kinetic friction as well, and these will be different from the coefficients of static friction for the same materials. These values allow us to calculate the magnitude of the kinetic frictional force acting on a sliding object.
Let's continue with free body diagram. What is free body diagram? It's a simple diagram that shows the magnitude and direction of all forces acting upon that object. For example, let's say I have this book sitting on the horizontal table. So you have a normal because there's a contact force between the table and the book, and you also have weight because of the mass of the book. So you have W and N in this free body diagram. So this is the example just now, and you have to know that the weight is equals to mass times gravity. The second example, let's say we have a box pulled along a rough horizontal surface. There's a key word here. This is a rough horizontal surface. So what it means? Correct. We have frictional force acting upon the object. So you have the box pulled to this side. That means there's going to be friction moving directed opposite the motion. So I have force pulled this way, and I have frictional force in the opposite direction. And as the same previous example, you're going to have weight because you got mass, and you're going to normal because it touched the surface of the plane. Now you have an inclined plane. So what is the difference here? It's actually the same, because we have force pulling upward here. So this is our force. Now, is this a smooth or rough? Yes, this is rough. That means you have a frictional force opposing the motion. So motion that way, the frictional force should be that way. Okay, correct. Next, the same thing just like now, we have weight still downward. Remember, weight is due to the gravitational pulling. So it must directed to the center of the earth. And then we have normal, which is perpendicular to the surface. So this is our surface. Perpendicular is that way. Okay. Now, what happens if I have two different objects here, but hanging? As I mentioned just now, remember, hanging object doesn't have normal or reaction force. So, the only forces involved here are the weight, obviously, and also the tension upward. Okay, tension is always opposing the load. What about the second one here? You have two kind of strings attached to this mass. Yes, you have tension, but they have a different tension. So, tension here is T1. Tension that one is T2. Okay, T1 and T2 are not the same value because they are not attached to the same string. Okay, be careful with that. Next, let's say I have this case for the pulley. So I have two objects attached to the same string, and this is a smooth pulley. So you have two objects. So two objects mean two separate free body diagram. So you have to draw M1 and then you have to do for the M2. So for the M1, I know I have weight 1 equals to mass times gravity, and also I have tension 1 because tension should be opposing the load. Okay? And then another free body diagram, which is for M2, you have weight 2 downward and also tension 2 upward. So in this case, T1, T2 are the same or not? Correct. They are the same because they're attached to the same string. So T1 and T2 are the same value. Alright, what about here? M1 and M2 attached to the same string. Okay, so you have two objects, means two free body diagram. So let's do for the M1 here first. Okay, this is the M1. Remember, this is smooth surface, so there must be no friction. So T1 that way, correct. You have weight 1 downward, correct. And also you have reaction or normal upward, okay, perpendicular to the surface. What about the M2 here? So M2 basically you have tension 1 and also you have weight 2. Okay, T1 and T2 are the same because they are attached to the same string. Alright, let's practice to draw more questions on free body diagrams. Hopefully you're gonna get more understandings later.